Hello everyone. My name is Sachin Ramachandran. I'm a graduate student at the University of Florida. This is the final project presentation for EEL 6825 pattern recognition. The advisor for this course is Dr. Tapping Oliver Wu. The project topic on discussion today is principal component analysis based multiple sclerosis detection. This is the presentation outline and what we'll be going through the presentation. So what is multiple sclerosis? We'll talk about the existing MS detection techniques, the drawback of the existing MS detection. We'll talk about the automated techniques and the phases of automated techniques. This is the proposed solution. We'll talk about what bias field correction is, why is it important for this project, and how it is used. We'll also talk about the types of bias field correction that we've used in this project. Excuse me. We'll also go on to talk about the research conclusions and the future work. So, what is multiple sclerosis? Multiple sclerosis is a disease in which the protective layers of the nerves are damaged by the immune system of the patient. So, what we refer to as MRI scans or magnetic resonance image scans help us visualize these damages to the nerves. For example, lesions are damages in the fluid attenuation, inversion, or recovery, also referred to as flare. They are basically identified as tiny and vivid spots. One significant point I'd like to make here is lesions and multiple sclerosis will be used interchangeably in the presentation so as to help you better understand the project. Well, there are a lot of existing MS detection techniques, most of which are being done manually by experts in the field. So these lesions are basically detected by experts who look for certain abnormalities in certain areas of the scan with respect to size, intensity, texture, appearance, etc. So what causes us to develop an automated technique? Well, the current manual process is time consuming because of the large number of MR scans that exist. One concern or one significant concern is the observer variability, where observing from different experts give us different results. Even though they help classify that multiple sclerosis does exist in a particular patient, the observer variability tells that there's systematic difference between different observers. So our automated technique will basically be using training data sets and test data sets. We'll be using two training data sets with FLAR, T1, T2, MD, and FA data. Training data sets contain information about lesions that are categorized by the experts in the field. So this is the sample raw FLAR that we'll be using for this project. Um, we'll be using a PCM model with log likelihood ratio. So this will help us classify each voxel. We'll also use a feature vector that will contain intensity of neighborhood voxels, the data histogram, and the MS probability atlas. We'll use the techniques of atlas registration and bias field correction. Then the training data set is basically used to compare and contrast the feature vectors between MS voxels and non-MS voxels. I'll talk about a voxel later in the presentation. So these are the phases of our automated detection. The training data set goes through the PCM method, the feature vectors, non-atlas registration, and the bias field correction. The test data set is tested against the training data set that goes through all these four phases. So what is principal component analysis? Principal component analysis is the procedure of converting a set of correlated variables into a set of linearly uncorrelated variables using the technique of orthogonal transformation. So we refer to the uncorrelated variables as principal components. PCA's major strength is it helps reveal the internal structure of the data in a way that explains the variance in the data. So the PCA method is basically used for this project. It's used to identify and classify voxels as a multiple sclerosis or a non-multiple sclerosis voxel. A voxel is basically a 3D pixel is what I would like to say. It's a three-dimensional element. So the PCA classifier is responsible for classifying a two-class problem, identifying and detecting the multiple sclerosis in MRIs. The two voxel classes are built from the training set of the MS and non-MS voxels. The PCA uses the feature vector because they contain the voxel intensities to classify the voxel as MS or non-MS. So the first step in this PCA method is to divide the method into two matrices, LX and GX. LX represents the MS voxels and GX represents the non-MS voxels. The matrices will be then centered with respect to the mean. We'll then combine PCA with singular value decomposition to get the eigenvalues and the eigenvectors. We'll then choose the top 99% eigenvalues, and the list 1% is discarded, and the eigenvectors are multiplied to both the data sets, and this will make the non-MS data orthogonal. As I already said, the key to any PCA method is to make the data sets orthogonal. Now that non-MS data is bit orthogonal, we'll have to make the MS data set orthogonal. So it's very similar to the previous step, except for the fact that eigenvectors are multiplied to data set after normalizing the variance to 1. So this step clearly shows you we normalize the variance to 1, and then we multiply the eigenvectors to data set. Now both the MS and the non-MS data sets are supposed to be orthogonal. So we again multiply the eigenvectors to both the data sets, and this will give us LPCA3 and GPCA3. We will merge all the PCA notations to one matrix called UTOT. The covariance matrix CGPCA3 can be computed from the GPCA3 data. So this completes a model, and we can now use this model to classify the test data sets. We'll use the concept of Mahalanobis distance to calculate the distance of the feature vector of a certain test data set voxel on the coordinates. Since a voxel is a three-dimensional image, we have three x, y, z and coordinates. So this is done to both the MS and the non-MS classes. A threshold is applied to the log likelihood ratio of the distances, and this will also help us get the binary MS classification of whether it is an MS or a non-MS. The threshold actually depends on what kind of log likelihood ratio you would like in the project. We have used a threshold of 0 to 1 here. Um, as I said, PCA uses feature vectors. So what are feature vectors? Feature vector is basically an n-dimensional vector of numerical features that represent some object. But the numerical features are not the only kind of features that can be. We can have other type of features also, but why we prefer numerical features is because it will help facilitate processing and statistical operations. Feature values correspond to pixels, so any kind of processing can be done on the image based on pixels, and in turn this will reflect on the feature vectors. So a key to any pattern recognition project is to identify unique features, and they are to be numeric in nature. The reason why we prefer numeric nature feature is to help perform a lot of mathematical functions and operations, and this will make classification better. So these two figures shows you a good feature and a bad feature. So a good feature basically identifies all the features in a particular class and distinguishes all the features in a different class. So these are all from the same class, these are all from the same class, both have been distinguished properly. But the bad feature, we have two classes, both classes are used interchangeably, and that's why this is referred to as a bad feature. So how do you use feature vector in our project? So PCA uses feature vectors to help identify and classify voxels. The voxels basically contain, or the feature vectors basically contain MR neighborhood intensities, which describe the appearance of that particular area of multiple sclerosis. We'll also use the derivatives of the voxel intensities, and these are added to the feature vector because the MS lesions are basically lines or binary large objects. Histogram provides the model about the low pass intensity details or intensity values for a particular region. So we would like to exclude false MS voxel detection. So we basically use the MS atlas probability and the location distance to the brain center, and hence these two are used as features. As I already told you before, a good quality feature vectors are essential for better classification of results. So we'll be using a total of 225 features that constitute the feature vector in this project. So this clearly details about the different features we use in the project. We'll use a total of 225 features that combine up to the feature vector used for this project. The third phase of this project is non-rigid atlas registration. MS probability atlas is used as one of the features. The atlas is constructed from the expert annotated lesions in the training data. The T1 atlas is affine fitted to all T1 training data sets. So by affine fitted, we mean we rotate, translate, and resize the atlas to fit all the T1 training data sets. So this is an example of the affine fitted atlas that we'll be fitting into the T1 training data sets. We'll use a non-rigid B-spline based technique or an algorithm, and white matter atlas is used to get a better alignment in the white matter area. The inverse transform of the atlas registration is basically used to align the lesion data sets of all patients, and then this is used to generate MS probability atlas, which we'll be using as one of the features in the project. So the non-rigid alignment that I was talking about previously, will be based on the method of freeform deformation with a B-spline algorithm or a grid. We will calculate error based on a concept called the normalized mutual information. So the alignment of the transform atlas, by the transform atlas we mean the one that is finely fitted to the T1 data set with a certain control point, can be described by the normalized mutual information C that will be referring to here, that is calculated using this particular formula. And as I said in the previous slide, error calculation is done with the NMI. So that's why we can represent this C as a function of E. So the E represents error here, the error measure. The alignment is always with respect to the highest error in highest error. So B would like to call the highest error in the gradient. So a gradient of a control point is defined as, or it's defined by shifting a control point in 6 directions: up, down, left, right, front, and back, and the calculation of error in the affected area for all the 6 transformations that takes place, the 6 shiftings. So this gives us the gradient, and the gradient can be computed as follows. Um, so these two formulas help you find the gradient in this particular situation. So this is an example of a non-rigid atlas illustration of with control points 25, 10, and 5 applied to the initial affine fitted brain lesion diagram I showed you. So as you can clearly see, you can find distinct differences once the non-rigid atlas illustration has been applied. Why is bias field correction necessary? MR scans generally suffer from slowly varying non-uniformity, also known as intensity inhomogeneities. The PCM method will also be influenced by the bias field because we have varying intensity problems, and these will influence the correlation values between the used features. So after applying the bias correction, you can see from this figure that the edges are brighter and the details are finer than the raw flat data. So there are three techniques we'll be using for bias field correction. One is using genetics, one is using atlas, and edge preserve filtering, which is simplest of all. So using genetic as a technique, basically this is used to correct non-uniformity with a single histogram peak. The radio frequency non-uniformity will basically broaden the histogram peaks. So this is used as a basis for the technique. A genetic algorithm is used to select, cross, or join and mutate or change a set of models. So I would like to call them intensity correction models. So this is a three-step technique as I already told about, and we iterate through this three-step throughout the whole process. So we select, join, and mutate the intensities for a particular group or population in the set. So we basically take a few groups from the population, and then we assess their fitness rankings. So the ones that have the least ranking are removed and are replaced by joining and mutating the remaining models. So the groups are then put back, or the models are then put back into the whole population, and the iterative procedure keeps continuing. The final population of 100 models is used to correct every size of data by following the iterative procedure we have previously defined about the bias correction has been achieved, and once the bias correction has been achieved, obviously uniformity has been achieved. So the next is to use the atlas. So different atlases like gray, white are fitted non-rigidly into the MR scan of the patient, and the combined intensity-based probabilities, or the probabilities from the atlas, help determine the bias field. First step is to fit the atlas non-rigidly, as already explained in the previous point. Next, we find a value with respect to its histogram data for each of the tissue types you'll be using for the detection. So the histogram is then divided by the total of all the individual buckets in order to obtain probability of intensities for the atlas types in the background. The atlas types and their probability are then combined. Next, we find the average intensity for each type, and then we'll select the pixels that have the topmost probability. So our key point here again is to compute the bias field. So in order to compute the bias field, we will divide them with the average calculated with the average calculated intensity. So once we have the computation of the bias field, we'll extrapolate them to the whole volume and then iteratively divide the bias field to correct the bias field in this particular technique. Edge preserve filtering is the most straightforward technique. It is basically used to preserve all edges that are sharp, or rather, I would like to say it will smoothen the edges and still keep the edges sharp. The technique is mainly advantageous when edges that are not sharp exist because that will cause distortions in the scan. So the MR scans are sent through a low pass filter. The MR scan is then divided by the scan that is being low pass filter. So the filter is then used to filter out edges that cause the bias to vary. So a classic example of a filter here is a Gaussian filter. Uh, so that can basically use to filter out edges that cause the bias to vary either above or below. So this filter helps preserve all the edges, even though they smooth the regions, and thus helps in correcting the bias field, as I already told in the previous slide. So these are the results for the project. I would like to just run through them and run through the code right now. So this is the MATLAB code. The example underscore classify underscore ms is the main program, which calls the other programs train underscore model and apply underscore model. The get feature vectors will basically help design the feature vectors for this project. So just running through this code. So as you can see, we basically retraining data set, combine the data to one image, and then we have a multiple sclerosis lesion marked by experts, and then we basically show the data training data set, and then we read training data set of patient two. We have that also marked by an expert here, and then we show the training data set, and then we make a matrix. These are the training feature vectors that will be used for this project, and we have a set of um, training vectors that can be tested against the test set. So this is the log likelihood model. Uh, the train model is basically responsible for the this train underscore model.m contains the whole PCA method. If you can see, there are two matrices L and M. We calculate the L mean and G mean with respect to the mean. We're using SVD with PCA, and also we calculate the limit the number of eigenvectors, multiply the eigenvectors, and then we normalize the eigenvectors for this particular situation. We talked about normalizing eigenvectors for MS based detection. And then towards the end, we also have something called as the centroid. So B tot is the total feature transformation vector we discussed, and this helps generate the covariance matrix from something called a GPCA3 that we have discussed previously. The apply model is basically it uses the matrices and means from the previous train underscore model, and this helps calculate the Mahalanobis distance to the global and local feature data sets, which are combined to a log likelihood ratio. And for this case, the log likelihood ratio, the threshold is 0.5 for this case. So I'll just run the code for you. So this is the first figure. It contains the flare of training set patient 1, MRIT1, MRIT2, and these are the lesions annotated by experts. If you can see, there are red spots here that mark the lesions annotated by the expert. We'll just wait for a couple of minutes for the other set of outputs to generate here. So our main aim is to correct the bias field also, and also make sure that you have a sharp edges in the images. So we'll be using two training sets, as I already mentioned. We'll compare the two training data sets we use and run it against the test data sets. So this is the training data set of patient 2. So as you can clearly see, even though training data sets 1 and training data sets 2 classified by experts help in finding the MS, there are significant observed variables if you notice here and notice here. Coming to our so this is the figure 3 is basically the output of our code. As you can see, MRIT1 is bias field corrected. It looks much brighter. The after the faces are applied, MRIT1 and T2 look much brighter. The edges are sharper. And comparing the threshold log likelihood on pixels, this perfectly helps us classify a multiple sclerosis. It helps detect the multiple sclerosis and helps the lesions. And if you can see, pretty much all the classified data by the expert and the classified MS by the automated technique are almost the same, and they work perfectly well. Going back to the presentation, um, so 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 clearly we have told that the automation technique takes care of what it is supposed to do. We have developed a feature vector and PCA based automation technique that helps in detecting lesions from FLAR and MRI scans. So as I already told before, the main motivation behind this project was to reduce the time and effort spent manually on detecting lesions. Even though these lesions were classified by experts, One significant problem that I illustrated in the result is the observer variability between different experts. So we use a PCA classifier, two training data sets, and one test data set was used. Um, Feature vectors were used for the automation technique. So this helped identify and classify voxels. The choice of feature vectors played a crucial role, as I told, because a feature vector is key to any pattern recognition project. Non-rigid atlas illustration was explained. The problem with the non-uniform intensities in MRScan was solved by implementing bias field correction using three different techniques. So the future work for this project might be to improve on the feature vectors to get a better classification. Uh, a lot of training data sets need to be introduced so that running any test data set would yield you the result. And we might want to have a separate methodology for identification classification of MS and non-MS data set may be used. Thank you for your time, and I hope you enjoy the project. Thank you.